In this tutorial, we're going to determine the camera orientation for two cameras that will be used in 3D motion analysis, and then set up a project-based coordinate system. The TEMA wand will be used. The orientation is based on an image sequence of the TEMA wand being waved around in the view of both cameras. We have 3 synchronous images, although only 2 are needed. The images are named left, right and middle, and we're going to bring them all 3 in together, and we're going to define the camera parameters for each one. All 3 sequences have been previously synchronized to the same time 0, so that frame 0 time is the same point in time for all of them. These images are dark because the exposure was set for the lights on the wand, and so it is difficult to see the operator moving the wand in the background. We will lighten the images later so that we can set a coordinate system up based on items in the background. You can check the synchronization on the Time Overview option on the View menu. If you need to adjust, there are 2 controls. This one determines which image has the focus as the master for synchronization, and this one can be used to reset the time on any one of the image sequences. Now we have the 3 sequences, and we're ready to do the wand calibration. All you need to do is go to the camera menu, then the wand calibration. We need first to set the distance between the 2 points on the end of the wand as calibrated in the factory. Then we just press the Go button to start. The tracking is totally automatic. If you watch in the top left of the dialog box, you will see the frame counter as it proceeds, giving only the number of valid frames. When the wand lights move out of the image or can't be tracked, we have invalid frames. We need at least 100 frames to calibrate. This was a 20-second sequence with nearly 1,000 frames. 2/3 of these were valid. Now we can skip to the end, and we can check the next button to see the results. The left camera has an XYZ position of 0 and roll, pitch and yaw of 0 degrees. The focal length has been recalculated and the mean 3D error is reported here. For the middle camera, you will see that the XYZ position coordinates and the roll, pitch and yaw coordinates are given relative to the left camera, and then those of the right hand camera relative to the left camera. So now we have all 3 cameras orientated in XYZ, roll, pitch and yaw. Now we will enhance the brightness so that we can see the background, and we will use the dry erase board on the wall in the background as a basis for the new coordinate system. Now we will add 3 points, and we will put them on the bottom rail of the board, which will be our x-axis, defined by points 1 and 2, and on the top left side of the board, point 3, and this will be used to complete the definition of the xy plane. We will use the show window to get an accurate position for each of the points. When we add these points to the next image, TEMA will draw a back projection line showing on the places on which he expects the points to fall. We will have to confirm the point location. The accuracy of this prediction is an indication of the accuracy of the 3D analysis. When we add these points to the third image, they will automatically locate themselves. Now we are ready to establish a new coordinate system. This will be based on these 3 points. We need to add the new system, set the system as static as the cameras are not moving, and set the frame in which we track the 3 points. Next we will define point 1 as the XYZ 0. We will define points 1 and 2 as being on the x-axis, and we put points 1 and 3 on the xy plane. If we now pull up a spreadsheet, we can check these coordinates. Note that the coordinate system we established was in one frame only, but is valid for all frames as the cameras are not moving. If the cameras are moving, then the 3 points need to be tracked in all frames and a dynamic coordinate system requested instead of a static one. Now we're ready to track moving targets and plot their 3D motion. As well as camera orientation, this process also carries out lens calibration. This lens calibration and camera orientation is not exported in a separate file. However, you can import that data into another test by importing from the archive file of this test, as with the relative orientation process. However, of course, the orientation requires that the cameras have not been moved, but the lens distortion is still valid even if they have.